strain condition.
What do you count?
So
What do you want me to get?
So session 3.
I know. Which one's yours?
That's it.
That
That one. That's right.
No, I'm not on it.
Okay, that's it.
Thanks, Neil. Thanks for the organizer for the invitation. And last time I talked about crack tip strain evolution in front of the crack tip under second clothing conditions. And this time I'm going to look at both ways, which is behind the crack and in front of the crack. I'm going to bring you back to the very boring subject that we seem to know everything about, which is the long fatigue crack situation. Because if I can say what happens in front of the crack, well, I consider that as a primary event. What happens behind the crack, we consider that secondary event. For most of the engineering material, if we look closely, the plasticity in front of the crack for a long crack is actually very considerable. I'm talking about for stainless steel, for example. We can have a monotonic plastic zone about 1 to 2 millimeters. So for small scale yielding to work, we need a crack as long as 50 times the plastic zone size. This pretty much excludes all the test specimens we normally use to do the testing. Therefore, what we need in front of the crack, with crack driving force, we need an elastic plastic parameter for a start. What happened in the process zone is probably at micro level, which is probably at the same scale as what happened behind the crack. Whatever mechanism we might have, okay, it's probably at the micro level. We talk about steady state crack growth, so we're talking about the crack growth rate 10 to minus 5, 10 to minus 6. So per cycle is about in the micron scale. Okay. But the current method is that we measure the crack closure, whatever mechanism it might be, and we measure the opening load. By no means this is a unique value I'm going to show you in a minute. We then go back to correlate the K, which may or may not, quite often may not be valid. So I think that we have quite a bit of problem in that. And the other problem is, whatever happened behind the crack tip, the secondary events, it impacts on the crack tip front strain and stress fields unclear and fast to us. So I think our work is in this direction, towards this direction, and trying to answer some of these questions. Just to give you some idea, we use DIC, which is the surface measurement, so measure plane stress, and the CT specimen. And in this particular specimen, you can't even see the full size of the plastic zone. Okay, so we look at the crack tip there. We're trying to look at the crack tip stream field both front and back. And we have standard CT specimen, cyclic loading, fatigue pre-crack. And we look at two different situations. The first situation is stationary crack. And that is, we apply the load so that within a limited number of cycles, there's no crack growth. And secondly, we look at the growing crack. In this case, we raise the load level and we allow crack growth. We calculate this more like steady-state crack growth. So we actually measure the image, the last bit of crack growth. I'm going to show you later on. We use the standard software, the vision, and the camera system here is that's the length, that specimen is there. So we can achieve the spatial resolution about 0.68 micron per pixel. So this is the raw data that I give you. I'm showing you the displacement in y direction, x direction, and the strain in y direction. To do this, we actually excluded the crack weak, and we learned this only by mistake. To start with, we included everything, and in fact, the wicked value is totally incorrect. So we did some finite element analysis to estimate the maximum COD which is about 40 micron. So we actually excluded that area, and this is the sort of result you get. It's not entirely symmetrical, as you can see. The subside size that we use is 33 by 33 micron. This is limited by the speckle distribution. So essentially, I think most people use this white paint, and then you have speckle on it. To do a quantitative analysis, you really have to know the scatter. So I think this is what we did before we ran analysis. And this is at zero load. We choose the image or region of interest is about 1 by half a millimeter. Okay. So we look at displacement scatter and strain scatter. The blue is behind the crack. This is the crack tip. The red is ahead of the crack tip. The behind the crack, the weak, the scatter always slightly higher than the front. But overall, for displacement, we are looking at 0.1 of a micron. And for strain, we are looking at between 0.3 and 0.4%. This is for the displacement, for the strain in Y direction, which is our interest. Now, to determine crack tip position is very important because we need to be sure which one is weak and which one is the front. And this is the method that we use. For the system, we do have a microscope that you can see the crack quite clearly. This is under no load. So we can trace the X direction first. And from that X direction, we're going down. This is the BIC image. We need to know where the crack tip is on the BIC image. So essentially, the method is to average the whole image size, the Y displacement. And that average Y, because there's no load, ought to be approaching 0. And that Y value would be indicative of the crack tip position in Y. So this is the crack that we treated. We look at 4 points in front of the crack tip and 4 points behind the crack tip. I think they were not battery. So essentially, the value of the strain and displacement is actually averaged over an area of 10 by 10 micron. Okay. On behind of the crack tip, we look at the 4 points also, and we use those points to look at the closure. We measure the closure at all 4 points. Okay. Also measure the closure at 2 different distances to the crack plane, 2 different Y's, that is. The distance between each point equals to the green side, which is 70 micron. Now this is the crack closure measurement. You probably can't see too well behind that, but what I can show you is these are the 2 diagrams. I can show you. These are the 2 measured at 2 different Y distances to the crack. And you can see they are more or less quite similar. But if you look at the different colors, these are the distance to the crack tip in X direction. And you can see at a glance the crack opening at different levels. It is not a unique value. So essentially what happens is the crack is peeling from behind, opening up. By the way, this is nothing new. Okay? Someone, Riddle, 1999 used compliance method already measured this. Okay? That's mainly good work actually looking at the surface as opposed to the bulk or 3D crack front. The crack opening load is not a unique value, it varies. So we run some finite element analysis. So clearly this is a linear elastic problem. We use a quite simple model. But the simple model does include both kinematic and isotopic hardening. And we use the same methods to calculate the strain, the same area to calculate the average strain. So this is the important diagram I'd like to show you. This is a normal strain, the same as maximum principal strain. Okay, so 0 would be the crack tip position. Negative here would be behind the crack tip. Positive would be in front of the crack tip. Now, at the first glance, if we look at the high load level, for example, part 2, the crack tip measured value correlate quite well with the FE result. By the way, the FE result has no closure because we only simulated for the cycle. So if the closure has no influence, that would mean the first two should have no influence. But what we registered with the closure measurement is, I think it's up to 0.46. That would be the oligo. Now, if you look at the oligo, it's here. The point for this is actually further down. You could say that's probably influence closure. But if you look at the cross, which is 0.55, and the cross is also here. So all I can say is, it is not entirely clear whether or not this closure influences the crack tip string field ahead of the crack tip. By the way, we probably remember the strain we have a scatter band about 0.4%. If you take a double of that, it's probably reasonable to say here is probably the data probably not so high. So what we can say is from this set of results, we cannot really say whether or not we have an influence on crack closure. The closure opening node changes so much, but also there's no conclusive evidence to say it has an influence of the strain ahead of the crack tip. Now I'm showing you some growing crack measurement. For this, we cheated a little bit. You can see the crack growth, the path is quite irregular. So what we did was to take the last bit, which is reasonably smooth. So instead we have to do the local coordination and do the transformation. We just look at this last bit, and we track about 8 points and look at the strain. So essentially we have the strain register as crack grows in situ, and we look at it when the crack tip gets to this point, line the idealized crack path 1, 3, 5, 7, and to see what the strain value is like. So this is what we get. So the crack tip now, A is at 0.1. So B is at 0.3, so C is at 5, and D is at 7. And if you look at this point, although this is measurement, some discrete point, you will see that the value is more or less actually similar, about 8 micron. And this indicates the crack tip position. And this value is actually similar to the value that we reported previously, and slightly higher, slightly lower K value. So they might have some meaning, I don't know, is for this particular theory. So to conclude, we say we could use PIC to look at string field, but to correlate the data and in the weight is quite difficult, or at least the resolution for what we get. So the normal strain and high crack tip seem to compare okay for the higher load level, but we don't know about the crack opening. All that influence on the crack tip, ahead of the crack tip, the strain field. And we think if we track this normal strain, we might have some idea about the